Use of finite element mesh in a structural model is very common. If you want to design a floor diaphragm using accurate design strip method or as a post-tension slab, then you need to model it using plate element. Design of concrete slab using plate results is much more accurate than traditional panel method, and for a complex slab geometry with opening, this is the only way. Also, if you want to design a basement wall or a shear wall, that must be modeled using plate. There are so many other applications of FEM, from foundation design to modeling a culvert or a silo. Plate mesh is used in all types of model. Instead, there are multiple methods available to generate a plate mesh, from simple grid method to advanced parametric model option. But each method has some limitations, and if you select an incorrect approach during modeling, not only your modeling time will be increased, but also the flexibility of further modification will be compromised. Hi, my name is Surajit Ghosh, and in this video series, I am going to discuss about different methods available in STAAD for finite element mesh generation, difference between these methods, and which method is more suitable for modeling. Also, I will discuss few modeling issues related to plate mesh and how to rectify those problems. Before going into the details, just want to inform you that in Connect Edition, a new modeling mode known as Physical Modeler is introduced, which is the best module to generate a FEM model. Personally, I prefer this module for modeling any structure with plate mesh. I'll cover this module later. First, I want to discuss how to add a single plate in a model. In Analytical Modeler, we can generate a plate using traditional grid method. This is similar to beam grid. We can select either a triangular or rectangular plate grid. Only these two types of plates are available instead. Depending on the element type, a grid is created, which we can further customize from this window. Like the plane of grid can be modified to XZ plane with required spacing in two orthogonal directions. Also, we can create an irregular or radial grid if required, and then use the cursor to add a plate by selecting the grid points. This is very basic approach. We need to add each plate element using grid points, and for a large plate mesh, this method is not at all suitable. This approach might be helpful if you plan to draw the entire slab or mat boundary using grid and later mesh it using other plate mesh option. In this series, I will use this 10-story building structure to demonstrate how we can properly model the slab and shear wall using plate mesh. I have already assigned all beam and column properties, and my intention is to model the slab at each floor level along with a shear core at this location. First, isolate a single floor, and I will generate the plate mesh in this floor using different methods. All the plate generation options are listed in the geometry ribbon. From here, we can select 3 or 4 node plate cursor and add plates directly in the model by selecting the corner nodes. Also, there is another easier solution to generate a single plate in each panel using Infill plate option. We can select few closed panels, means floor panels which are bounded by members, and then use this option to generate a plate in each panel within that specified boundary. This option will not work if you select an open panel. You can notice 5 unmeshed plates are created at this location, one for each panel. Now the question is, we can easily generate plates in the entire floor using any of this approach? Then why a plate mesh is required? Well, there are several reasons. First one is related to modeling error and incorrect force transfer. If you look at these plates, you can notice that the plates are generated inside each closed panel, and for these panels without a secondary beam, the plates are properly connected. For this panel, we have a secondary beam, hence two separate plates are generated, but a complete plate is generated in the next panel, which does not share a connection at this intermediate node. When a load is applied on a plate, that load is transferred to other member or plate through the corner nodes. If two plates are not connected through a common node, then load from one plate is applied on the edge of the next plate. Also, as this is not a common node, this plate does not have a fixity at this location. To illustrate this, I have created a simple model with two plates not sharing a common node and applied a plate pressure load in downward direction. In the post-processing mode, check the deflection diagram. You can notice that at this node, there is a huge deflection in vertical direction. Same is reported in the table. This suggests that the small plate is not supported at this node and can move freely. This unrestricted movement of the plate generates an unstable condition. This modeling problem is known as plate-to-plate connectivity issue. If you go to Utilities, Plate, and Plate Connectivity tool, you can notice these plates are highlighted and program informs that there is a connection issue which will provide incorrect analysis result, like large deflection or incorrect force transfer. To solve this issue, we need to generate plates in this panel in such a way that all the plates have a common node at this junction. We can remove this plate and add three triangular plates in this panel connected to the common node, which will establish proper connection with the other plate. And this plate arrangement will remove the plate-to-plate connectivity problem. There is another modeling problem at this junction. This secondary beam and the primary beams are connected at the edge of this plate, and similar to the plate connectivity issue, these beams don't have a connection or support at this location, as there is no common node between the beam and the plate. This is known as beam to plate connectivity issue, and if you go to Structured Tools, Beam Plate Connectivity tool, this problem will be highlighted. See, there are three connectivity problems with this plate, as these beams are not connected through a common node. At this junction, beam and plate will behave as an individual element, not as a monolithic entity, which is not the realistic scenario. Modeling of a plate will be proper only if the plate shares a common node with all the members and plates located in the adjacent area. This means any existing plate node or beam end must be selected as a corner node during new plate generation. For a large irregular panel with haphazard beam layout, manual adjustment is very tough. Also, no warning is reported in the output file for this, though this is a major modeling issue. Only way to identify these problems by using the connectivity check tools from GUI. Just to summarize the connectivity issue, these plate arrangements are incorrect as one or more plates are not connected through a common node. This problem can be modified by dividing the plates in smaller pieces, by selecting each common node as a plate corner node. Similarly, these beam plate arrangements are incorrect as one of the beam end doesn't have a connection with the plate corner node, and this can also be modified by introducing smaller plates which has a common corner node at the beam end. Apart from these connectivity issues, there is still another major problem. To demonstrate this, I'll use this simple tabletop model where the plate is rested on the beams. I have applied a plate pressure load to replicate the gravity load. Imagine this as a floor slab which rests on the beam, and as per the normal force transfer mechanism, we can expect this plate load will be transferred to the supporting beams and then to the columns. So if the model is correct, then these beams will be subjected to moment or shear. If you go to post-processing mode, from the deflection diagram, you can notice there is an out of plane deformation of the plate, but the beams are not deflected. If we go to member force page and switch on the BMD and SFD, from the force table as well as from the diagrams, you can notice that there is no bending or shear, which means load from plate is not transferred to the beams. The reason is, as there is no intermediate connection between the plate and beams, no force is transferred at any point of the beam. I have already mentioned that force from the plate is transferred through the corner nodes, and at the corner location, this plate is supported directly on the columns, which means force is transferred from plate to the columns. This is a faulty condition, and we need to modify the model in such a way that there are intermediate connections between the plate and beam through which force will be transferred. And for that, we need to mesh the plate. When we mesh this plate, it is divided in small segments along with the beam, and these segmented plates and beams have proper connection. At each beam plate junction, force will be transferred on the beam as a nodal load. And if you consider the overall member, the nature of the load is like a UDL. This is one of the reasons why we mesh a plate during modeling. There is another major reason from finite element analysis point of view. With fine mesh, accuracy of the plate results increase. I will discuss this in future. Anyway, from these examples, you can easily understand why we should avoid modeling the slab using a single plate. This model with isolated plate is structurally erroneous and incorrect. How to generate a plate mesh properly, maintaining all connections, that I will cover in the next video. Stay tuned and thanks for watching.